Hello everyone and welcome to the National Environmental Science Program Climate Systems Hub webinar, When Tropical Cyclones Come to Town, Are Our Buildings Ready? For those of you I haven't met, my name is Ramona Della Pozza and I'm a knowledge broker with the Climate Systems Hub, working with the University of Tasmania with a team of knowledge brokers in state and territory governments. I'm looking forward to today's webinar because growing up in Innisfail, I've experienced the impacts of tropical cyclones firsthand and the devastating impacts they can have on our homes. The timing of this webinar comes at the end of the tropical cyclone season, and it's been an active one this year with 39 tropical lows, 11 tropical cyclones in the Australian region between October 2025 and April 2026. 4 of those tropical cyclones have crossed the Australian coast and impacted our communities. Our most recent experience with Tropical Cyclone Narelle worried communities in Queensland, Northern Territory and Western Australia over almost 2 weeks. And that was only the second one on record that has crossed in 3 states, crossed the coast in 3 states. So it's a good reminder that we need to understand the risks of tropical cyclones now and in the future. So before we begin, I'd like to acknowledge the Wurundjeri people who are the traditional custodians of the lands where I'm joining you from today. We pay our respects to their elders, past and present, and I'd also like to extend respects to all Aboriginal and Torres Strait Islanders joining us today. The Hub recognises the important role that traditional knowledge plays in understanding Australia's climate. So just as background, the Climate Systems Hub webinars are designed to provide an opportunity for sharing and learning. And we've had a great range of presentations and you can find all these recordings on our website, so please have a look. A few housekeeping things before we begin. The webinar will be recorded. The link will be available from the website after the webinar and will also be emailed to you that have registered. We encourage you to ask questions, and this can be done by typing them in the Q&A function on your screen, and we'll address as many questions as we can later in the session. I encourage you to get your questions in early. We don't have time to answer all the questions all the time. So in today's webinar, as I mentioned, we're bringing together climate science with wind engineering. We're lucky to have Dr. Hamish Ramsey to explore how tropical cyclone risks may change in the future, and Dr. Jeff Borton to help us understand the implications of this changing risk on our communities. So I'd like to warmly welcome our first speaker, Dr. Hamish Ramsey. Hamish leads the extreme weather and climate team at CSIRO. He works collaboratively with stakeholders to better understand climate change impacts on extreme weather events. And Hamish also co-led the NESP Climate Systems Hub project, Regional Climate Change Guidance for Local Action. And he'll share some of that research with us today on past and future trends of tropical cyclones. Over to you, Hamish.
Thanks very much, Ramona. Can you see my screen or not?
Not yet, not yet.
Oh, hang on.
You've got to do that.
Okay. How about now?
Yeah, perfect.
Great. All right. Thanks very much for the introduction. So if I can get to the next slide. Okay, great. Okay, so this next 12 minutes might feel a little bit like a sort of tropical meteorology 101 class, but I thought I would start with a global map of tropical cyclone tracks from 1980 to 2025. They're coloured by maximum wind speed on the right-hand side in units of knots. And you can see that the warm colours basically are the most intense, show the most intense cyclones. So the Northwest Pacific is one region that experiences a lot of intense cyclones. But of course, Australia and the Southern Hemisphere are no stranger to intense tropical cyclones either, which is the point of this webinar. And the main point of this slide is that TCs or tropical, I'm going to use TCs and tropical cyclones interchangeably, but Tropical cyclones tend to lose strength as they move away from the equator and down to the poles as they encounter lower sea surface temperatures and strong atmospheric winds, especially in the form of jet streams. Okay, so I've just shown you a map of tropical cyclones, and it turns out that there are very specific conditions that support strong tropical cyclones. And so here I've got essentially 4 thermodynamic conditions and 1 dynamic. So probably the most intuitive to people on the call would be that they form and track over relatively warm oceans, hence the name tropical cyclones. And these warm oceans provide necessary heat and energy for tropical cyclone development. They also need relatively deep water because tropical cyclones tend to churn up cold water from below, and that can weaken tropical cyclones if the water's not deep enough. High potential intensity, which I'll talk about in a second, and this is something that I'll show later in terms of some of the limits, poleward limits on how far south tropical cyclones can go in the southern hemisphere. High relative humidity, obviously away from land. Once they hit land, they weaken very quickly. And from a dynamical perspective, they thrive in environments of weak vertical wind shear, which means very small differences in wind speed and direction with height. So on the right-hand side is a map of what I just referred to as potential intensity. You can see, well, people who have looked at sea surface temperature maps in the past would see that the potential intensity looks a lot like the sea surface temperature, but it's different because in addition to being dependent on the sea surface temperature, it also relies on atmospheric temperatures. Some people describe this as a kind of a speed limit for tropical cyclones. So this is really the upper limit of tropical cyclone intensity given ocean and atmospheric conditions. And it tends to decrease as we move away from the warm tropical waters towards the poles. And so this is one factor that really limits tropical cyclone intensity as they move south. And importantly, this limit has been increasing in recent decades, and we expect it to continue to increase with global warming. Okay, so there's lots of different recent trends of tropical cyclones that we could talk about in this webinar, but probably the most relevant to Jeff's presentation coming up next is this idea of poleward migration of tropical cyclone peak intensity. So back in 2014, there was a pretty famous paper that was published in Nature, and they basically showed trends in the position of tropical cyclone maximum intensity around the globe, but including the southern hemisphere, and showed that the locations where tropical cyclones reach their peak intensity have been shifting southward or poleward around the globe since about 1980. And this is consistent with estimates of tropical widening over the same period, or some people might have heard of an expansion of the tropics, but they made no specific attribution statement to climate change in the paper. They just simply reported the trends that they had seen at the time. And this intensity metric has been the focus of many studies over the last decade, so particularly in the Northwest Pacific around Japan. But it's certainly inspired a lot of research since this paper was published. So back in 2020, the Insurance Australia Group and NCAR collaborated to release a report, Severe Weather in a Changing Climate, and they looked at this metric in the Australian region, and they found that the strongest trend in this metric was in the Coral Sea region. And so that's what this graph is showing you here. So there's latitude on the y-axis, year on the x-axis, and you can see a poleward trend or a increase in latitude with time in the Coral Sea. But there is a lot of variability around the trend. So in any given year, you can see tropical cyclones can reach their peak intensity at 10 degrees south or at 26 degrees south. Let's pose a question. Is the latitude of peak intensity, so this intensity metric that a lot of people have been looking at for the last 10 years, is it actually a useful metric for coastal risk assessment? So one issue with the latitude of peak intensity, or LMI, some people call it, is that it's fundamentally relative. It makes no difference whether a storm is a Category 1 or a Category 5. It only matters that it's reached its peak. So this has limitations when we're trying to understand things like wind damage to buildings, which Jeff will talk about next, because again, it's a relative metric. And so, one thing that came out of discussions with the Standards Australia Wind Loading Subcommittee and other stakeholders and collaborators was that, this metric has limitations for understanding exposure. And the recommendation was to consider winds along the entire track rather than just one point of peak intensity. On the right-hand side is an illustrative example of this difference for Tropical Cyclone Hamish in March 2009. You can see that the peak intensity occurred just east of Townsville, but the destructive winds went further south down towards Bundaberg in this case. Okay, so with that in mind, what factors really limit intensity of tropical cyclones as they move southward? So it's basically the opposite of what I described earlier in terms of the conditions that support strong tropical cyclones. So one big limiting factor is relatively cool oceans. So we sort of know this intuitively as tropical cyclones move south, the sea surface temperatures decrease, and that provides less and less fuel or energy for cyclones. Low potential intensity, which I'm going to talk about soon, that's very related to sea surface temperatures, but again, it also includes atmospheric factors. So it's a slightly more technical perspective, but I would argue that it's a more accurate way of looking at the thermodynamics rather than just the sea surface temperature alone. And high vertical wind shear. So this is usually associated with the subtropical jet stream. So some of you may have heard of this. I'll talk about this soon. Basically, tropical cyclones don't like strong winds in the atmosphere. It's sort of funny because they produce violent winds, but they don't like strong winds. They thrive in kind of calm tropical conditions. And the issue with tropical cyclones when they move south is that they typically encounter these jet streams. So for the next two slides, I'm going to focus on one thermodynamic variable, the potential intensity, and one dynamic variable, the vertical wind shear. So this is a map basically of the cyclone tracks that I showed earlier, so colored by intensity. And you can see the boundary of potential intensity of about 40 meters per second is a sort of a lower threshold, thermodynamic threshold for tropical cyclones in the current climate. And of course, some tracks go south of this boundary, but at this point, the cyclones have already transitioned to become extratropical lows or subtropical lows. They're not technically tropical cyclones anymore, but the forecasting agencies will continue to track them down towards New Zealand, for instance. One thing that's interesting is that if you look off the east coast of Australia, the thermodynamic favorable condition of potential intensity above 40 meters a second, so this area just here, it sort of dips down, which means that the thermodynamics are actually relatively favorable off the east coast of Australia. That isn't the main limiting factor. Instead, the main factor that prevents tropical cyclones from usually occurring in this region is the dynamics. So in other words, high vertical wind shear or the position of the subtropical jet, for instance. And we saw this in the case of Tropical Cyclone Alfred, which I'm going to show in a second. So yeah. And so another thing I should point out is that this is just an average depiction over 40 years. On any given day, the jet stream can sort of meander south or north. And when it's south of the Tasman Sea, that's actually quite good for tropical cyclones in the sense that they can continue in terms of their intensity. But once when it's in this position, it generally destroys them or moves them further out to sea. Okay, so here's just a depiction of both this thermodynamic limit, the potential intensity of 40 meters per second, and the vertical wind shear overlaid. And again, you can see that the thermodynamics north of this kind of magenta boundary is favorable, but the dynamics aren't. One important point I should make is that both the favorable zones of potential intensity and the favorable zones of weaker vertical wind shear, so kind of north of this boundary, north of this Siam boundary, are gradually moving polarward with warming. So that is, that is something we've seen in both models and observations, and we expect it to continue in the future. Okay, so I mentioned Tropical Cyclone Alfred before, and as many people would be aware, it travelled quite far south compared to other systems. But interestingly, it weakened. So it went from a Category 2 to a tropical low in this region at about the same latitude as Brisbane. And this is because at this point, the tropical cyclone started to interact with this strong vertical wind shear, or the subtropical jet, which I mentioned earlier. And you can see this in the satellite image by the fact that most of the thunderstorm activity and cloudiness is off to the south side of the cyclone, so it becomes very asymmetric. And this is kind of a telltale sign that that strong winds are starting to interact with the cyclone and essentially tear it apart. It did regain strength as it moved west towards the coast, but by this point, a lot of the damage had already been done in terms of the structure of the cyclone. Okay, so almost done. Even though Alfred was a wake-up call for southeast Queensland, it's certainly not, I should say tropical cyclone risk is not new to the region. There's been a number of impacting tropical cyclones all the way back to 1954 and probably earlier, including the Great Gold Coast Cyclone, which I think Jeff will touch on, Cyclone Dinah in 1967, and Tropical Cyclone Zoe in 1974, to name just a few. But that being said, tropical cyclone observations have improved over time. So basically from about 1980, which is when GMS satellites were launched, that sort of makes the most reliable part of the record. So before 1980, there's a bit more uncertainty, especially for cyclones that were well out to sea when we didn't have the satellite technology to observe them. An important point is that the regional risk has increased largely due to growing coastal exposure and development. However, any poleward shifts in tropical cyclones will certainly amplify this risk that's been caused by sort of explosive development, coastal development in this region. So second to last slide, just briefly, the IPCC AR6 Working Group 1 put out a schematic in their last global report for tropical cyclones. And actually, one thing I haven't talked about, but that's very important, is the fact that tropical cyclone rainfall is expected to increase with warming by quite a lot. It's actually the one metric that we're most concerned about. So, you know, things like flooding from tropical cyclones. There is an increase in strength. So in other words, an increase in wind speeds expected. And again, that's because this idea of potential intensity is expected to increase with global warming, and it's already increased in the last 40 years. And in terms of frequency, we expect decreased or potentially even unchanged frequency. Okay, but there is larger uncertainty in kind of regional projections, so especially around Australia compared to some of these global changes that we expect on the whole. Okay, so just finally, key messages and implications. The southward extent of Australian tropical cyclones is controlled by regions of favourable potential intensity and vertical wind shear, among other factors, which I didn't go into. These regions are gradually extending polarward with warming. So that's the first point. And perhaps more importantly, tropical cyclones respond more strongly to regional patterns of climate change than to changes in the global mean climate. So these regional changes, including changes in potential intensity and vertical wind shear, are highly variable in space and time. And that makes the interpretation and attribution of tropical cyclone trends difficult, especially when we're looking at a relatively short record of 30 or 40 years. And just finally, as I said in the previous slide, the risk of tropical cyclones is not new to southeast Queensland and southwest WA, but global warming is amplifying this risk. And that's due to rising sea levels, a warmer atmosphere, which can produce more intense rainfall, and warmer oceans, which result in higher potential intensity and increased wind speeds. So yeah, so that's it. I might hand back to you, Ramona, and yeah, happy to take questions later. Thank you.
Thanks, Hamish, for helping us to understand what controls how tropical cyclones form and also how this might change in the future. I think that was a great explanation. There'll be time for questions at the end of the Q&A. So please, at the Q&A session, so please keep putting your questions in the chat for us so we can answer them later on. I'd now like to welcome our special guest, Dr. Jeff Borton, to help us understand how even a small southward shift in tropical cyclone behaviour could expose more buildings and people to damaging winds. Jeff Borton is an adjunct associate professor at the Cyclone Testing Station at James Cook University. Jeff's worked in government, the private sector and universities during his 45-year career as a structural engineer. He's also contributed to changing codes and standards to improve the performance of buildings under wind actions. So we're very lucky to have Jeff here to help share his expertise. I'll let you share your screen now, Jeff, and over to you. Thanks.
Yeah, actually, if you can share it for me, that'd be really good. Click on the share button. It
looks like it's working now, so.
Magic, great.
Yeah, thanks.
Thank you. So my role here is to look at what's happening on the ground. So Hamish has spoken about what's happening on the atmosphere. How does that affect the way we live? And I'd like to start off by looking at the way we design buildings. So typically buildings are designed for a reasonably long life. We might build a building now, but we hope that it's in place still in the mid-2070s. So typically our expectation is a 50 to 100-year life for a building. In other words, what it's going to see is the winds not from today, but the winds over the next 50 years. But our wind standards, AS NZS 1170 Part 2, rely on historical data. And as Hamish has shown, we've got a lot of historical data that's valid for the last 50 or so years. So we're using that to estimate the loads we're going to be designing for, but the loads the building will see are the next 50 years or so of the building's performance. Okay. So let's think about how wind does affect buildings. And essentially, when the wind is blowing really, really hard onto a building, it's tending to push in the wall that it hits. So it's tending to push that wall that's shaded red in this picture in towards the building. As the wind is trying to push that wall in, it can't because the building's there. It has to bounce up and over the building. So as it leaves the top of the roof, it sucks the air that's sitting over the top of the roof out of that space and causes a negative pressure or a suction on the roof. And that suction can be many, many tons of force tending to rip the roof off. So that we have the basic external pressures on the building tending to lift the roof off, and we've got to have some really serious connections between the roof and the walls to prevent that from happening. And it happens really quickly. Look at this video here, and you can see just how quickly the roof comes off. And from a different angle, it is really, really fast. And it's really, really scary. So in designing buildings, that's what we're trying to avoid. And just summarizing, up the top here, we've got a picture of a roof that has come off a building. We've got uplift loads tending to pull roofs off, and we've got to counter those loads with really strong connections within the building. And then we've got lateral loads, and these buildings have been rolled along the ground, and that's due to the lateral forces on them. When we're thinking about what we've been talking about is the external pressures. But in designing a building, we also have to consider what is happening inside the building as well. In the top picture there, you can see a building that has got all of its windows and doors intact. And I've got a small cardboard model here that you might be able to see in the shot as well. When the wind is hitting this front wall, it's tending to push it in. And if a door should break on that wall, then that lets that high pressure air on that wall into the building and it blows the building up like a balloon. It's tending to push up on the underside of the roof, and it can almost double the loads on all of the connections that are holding the roof down. So if we've designed for this really strong pressure on the inside of the building, which we call internal pressure, that's not a problem. The strength in these fasteners will hold the roof down. But if we haven't designed for that and that door does get broken, we've designed for a situation in which there's no internal pressure. Now we've suddenly got some. It's increased the loads on the fasteners and the roof has failed. The other important thing, and Hamish has touched on this, is wind-driven rain that happens at the same time as the wind is really howling and causing problems for the building itself. You can see in that video that the rain is being dragged up the roof. The water is not running down the roof, it's running up it. It can go through flashings, through closed windows, through any kind of damage to the building. Once it gets inside the building, then it makes the ceilings soggy and the ceilings can collapse. And in all three of these pictures here, the outcome is the same. The ceilings collapse, the linings are ruined. And in this case here, there was no structural damage at all. It just came in through the flashings. In these others, there was structural damage. So you can see water damage doesn't need structural damage to happen. So when we're thinking about designing, there's two zones in Australia, or there are 4 wind zones in Australia, and 2 of them, regions C and D, are the ones through the tropics, which we've traditionally said are the cyclone regions. So that this map here has this red line that separates out the cyclonic regions from the non-cyclonic regions. I want to now think about a cyclone, and this is Cyclone Seroja that followed this green line here, and naughtily, it was a very naughty cyclone in that it didn't obey the map and it went south of the cyclone region. So there it is. It's crossed over as a Category 3 tropical cyclone in April 2021. And here's a picture of a part of its damage. In this case here, the branch caused some windows to break on the windward side of the building. Now, we've seen that before. That doubles the pressures on the inside. Because this region wasn't a designated cyclone region, there was no requirement to design buildings for that extra internal pressure. And even though the wind speed was less than the design wind speed by a reasonable amount, it was about 80% of the design wind speed, the roof took off because it couldn't cope with the extra load from that internal pressure. That wasn't the only house. About 30% of buildings in Kalbarri had this kind of damage. In this case here, those doors blew in, and that was enough to give us some internal pressure that started lifting the roof off. As well as that, every time a roof disappears, that increases the wind-borne debris load that is flying around, so that now it's not only the wind blowing windows in, but it's big stuff that's crashing into the front of the building. It will always hit the windward side of the building, and if it causes damage, that lets air into the building. So that wind-borne debris exacerbated the problems with internal pressure, and that's why around 30% of buildings suffered reasonably extensive roof damage in that event. The Standards Committee took this into account, and in 2024, they said that this green area through which Cyclone Seroja had happened is obviously now a cyclonic area, and it changed the cyclonic boundary, which was this red line that we were looking at here, to recognise that it could also transition. Cyclones do also affect wind region B2, which is this green region right round to Bundaberg. So now the wind or the boundary between the cyclonic and non-cyclonic regions is that red line. And that leads us to this particular part of the country here. That is also a wind region B, but it's wind region B1, not designated a cyclone region, and so there's no requirement in that area to have design for that high internal pressure. So we ask ourselves, Was Cyclone Seroja unusual? No, there were lots of cyclones, and this is an excerpt from the cyclone track map showing that there were lots of cyclones that went through this area over the last 50 years. If we look at the other side of the island, we can see, yes, there are lots of cyclones that have gone through this area, and that's this area on the map over the last 50 years as well. This red line is the one that Hamish has already talked about, Cyclone Alfred. And Hamish has given you the background on Cyclone Alfred. Its wind speeds were around 100 kilometres per hour, so that the wind speeds were approximately 50% or a little around 50% of the design velocity through which buildings had been designed, for which buildings had been designed. The big problem wasn't structural, it was rainwater ingress. So the Insurance Council of Australia's website reports $1.7 billion of claims for that event. And it's primarily due to rainwater coming into the building envelope, through the roof, through windows, all over the floor, and even through the walls. So that rainwater ingress was the main problem for that event. If we compare Alfred versus Seroja, both of them had big problems with rainwater ingress. But in terms of structure, we were struggling to find too many places that had wind damage to roofs after Cyclone Alfred. 100 kilometres per hour wasn't enough to induce it, but 166 kilometres per hour gave a heck of a lot of roof damage. Both of these areas were not designed for that full internal pressure. The scary thing about Cyclone Alfred was that when it was out here, it was predicted to cross with wind speeds of 140 to 155 kilometres per hour. That's significantly more and a significantly higher wind load on buildings than the 100 that it did cross with. And its outcome may have been much more similar to Cyclone Seroja's than what we saw when Cyclone Alfred did actually cross. So revisiting these cyclone regions, this is where it was before Cyclone Seroja. After Cyclone Seroja, we became aware of the fact that this green region, wind region B2, is also cyclone prone, so that the standard was changed to classify that as a cyclonic area. In light of what Hamish has been saying, we need to think seriously about where these southern boundaries sit for our cyclonic regions. Because if we get serious cyclones south of that region, it's going to cause the same kind of damage that we saw in Cyclone Seroja. So where should that southern boundary be? And anticipating the future, we're thinking about southward movement of tropical cyclones, and that's a really important consideration for the location of those lines. But wait, we're not completely in the dark. We've had it happen before. So if we think about the Gold Coast cyclone in 1954, around 30 people were killed in that cyclone. Hundreds of buildings lost their roofs in that cyclone. The storm tide meant that the waves went over the main north-south road at Kirra Beach down near Coolangatta, and that houses were flooded to the rooftop at Macintosh Island, which is midway between Southport and Surfers Paradise. So it was a serious event, Category 3, causing loss of life and certainly very significant damage to buildings in this area in the past. And likewise, on the western side of the island, Cyclone Albi in 78 was a Category 3 tropical cyclone when it went south of where the current cyclone boundary is. So it was the same strength of cyclone as the one that hit Kalbarri up here in 2021. And it caused, again, hundreds of buildings to lose their roof, storm tide that's depicted in both of these pictures here, And because the rain was on one side of it, as it had undergone extratropical transition, it also prompted bushfires. So finishing up on this map here, this is a map of cyclones over the last 50 years, cyclone tracks over the last 50 years in Australia. And you can see there is no golden rule that says cyclones cannot pass this line. There's a soft edge to the cyclone behaviour region. And yet when we design, we've got to make a binary decision. Are we designing for full internal pressure or not? So it's a binary decision, and that requires us to have a hard edge to our wind regions. And that bright red line on the map is the current cyclone region. In answering the question, where should that region be to cover us for the next 50 years? It's a really important question. That map is historical. What we really need is a map of where the cyclone tracks are going to be over the next 50 years. And it's the work that Hamish has been doing and people that are working with Hamish on the actions of tropical cyclones in subject to climate change that is really, really important in us answering this question. It's a really important question for us to answer as a community to ensure that our assets are protected, our lives are protected, and that the future is one in which we have anticipated the loads that are going to be likely to happen over the lifetime of the buildings that we are designing and building right now. Thank you.
Thank you so much, Jeff. That was a really good illustration of how devastating the impacts of tropical cyclones can be when houses are not designed to cope with them. And we really love your model house, so I hope everyone got to see that. It's good in action. Lots of surprised comments and reactions on the screen when you're showing all those photos. So yeah, thank you very much. Now it's time for questions. So we've already got some questions coming in. If Hamish, you want to come on screen as well, and we can, there we go, I've done it. And we can go through some of those questions, and I'll start by asking you, Hamish, actually, and it relates to one of the questions that I saw in the chat as well, is that you mentioned that regional climate change is important for understanding the changes to tropical cyclones in the future. And as Jeff said, that's really important for us to understand the risk going forward. Can you give us a bit of an explanation or give us an example to illustrate what you mean there?
Yeah, sure. Thanks, Ramona. So yeah, it's actually a really important point. So when we look at the way that oceans have warmed, not just in terms of future projections, but also the last 30 or 40 years, they've warmed in patterns. So it doesn't just warm evenly throughout the tropics. There's warming or changes to the sea surface temperatures that can look a little bit like what we see in an El Nino year, for instance. So I know this year we're moving into potentially a very strong El Nino. And these Pacific patterns can have kind of implications for tropical cyclones in our region, because the Pacific El Nino pattern, for instance, sort of modifies the whole Pacific ocean temperature pattern. It's not just where El Nino is happening near the equator. So yeah, so look, that's, I think, yeah, and certainly what we've seen in our own research is that, and in our other published papers, is that tropical cyclone intensity and other changes like rainfall are quite sensitive to these regional patterns of warming. So it's important to sort of zoom in and look at, what might be happening in the Coral Sea, or what might be happening off the northwest coast of Australia, for instance, rather than just kind of looking at the global average. Yeah. So.
And yeah, thank you, Hamish. There was a question in here particularly asking about the tropical jet, and is there a risk of it completely breaking down in the future? Would that increase the risk for Southern Australia?
So yeah, it's a really good question. Honestly, the subtropical jet dynamics is out of my area of expertise. But I know people are certainly actively researching this question. So not just kind of the average position of the jet, which is what I was showing you on the map with those blue arrows, but yeah, that's a really good question. So certainly if it was to break down more and become sort of more volatile in its or more variable in its position, then that would certainly provide opportunities for tropical cyclones to move further south than normal, because they're less likely to be disrupted by the strong winds. And that's certainly what we sort of saw with Tropical Cyclone Alfred. It actually recovered a bit. So the animation that I showed before, you could see this sort of disruption. The cyclone started to become asymmetrical. All the clouds got pushed off to the south side of the cyclone, but then it actually recovered a little bit. So the jet did weaken at one point or shift south. And that allowed, the cyclone to sort of try to recover. But by that point, as I said, a lot of the disruption had already been done. There's always a battle between the warm current off the east coast of Australia, the Eastern Australian current, which provides fuel for cyclones, and the jet, which is pretty hostile. So, yeah.
Yeah, great. Jeff, is there anything you want to add to Hamish's comment?
Yeah, the other thing, I guess, about Cyclone Alfred was that while it was starting to regenerate, it was partially over land, and it was moving closer to the land, so that was cutting the fuel off as well. So it was not the conditions weren't conducive to it regenerating, and the critical thing was that it crossed as an ex-tropical cyclone. So that the effects that were felt in southeast Queensland and northeast New South Wales were the effects of an ex-tropical cyclone. And we really dodged a bullet with that one.
Yes. Yeah. You don't have to tell me twice, Jeff. Yeah, I understand. A question for you, Jeff, actually, that's come up is you had been talking about how we need to change, we need to change the wind design standards. How hard is that process? How difficult? What are some of the barriers to doing that?
Yep. It is a reasonably complicated process. In order to change a standard, you have to have some really good science. You have to have something that is almost irrefutable, that says that this is the science that supports that change. And an economic case has to be put for it. So, for example, to increase the tie downs between the roof and the wall that is going to prevent roofs from coming off requires a little bit extra cost, so that it recognises that there's going to be increased construction costs. That an argument has to be presented that the foregone losses by doing that are going to be much bigger than the cost of actually doing it. So we're presenting a cost-benefit study for the whole of the country, if you like, on the basis of any change that has to be put forward. If those two things align, really good science and an economic case, then that argument is presented to people that make the decisions as to whether or not the change goes through. But there are a number of different levels of committees that have to embrace those changes, support those changes in order for them to go through.
And to add to that, there's a question actually that's just come up saying, is it significantly more expensive to build wind-safe houses, or could you make any comment on that?
Yeah, it is a little more expensive, but it's not as expensive as you might think. So it's a question of increasing the strength of the tie downs, increasing the strength of the windows to cope with those higher differential pressures. And on a typical house, it's of the order of a few $1,000s or thousands of dollars extra that has to be spent. Typically something around 1% or between 1 and 2% of the cost of the house. So it is an increase. It's not a prohibitive increase, But in terms of the potential savings, if you've got a house which after a tropical cyclone has been through looks like this, that's still an asset for the community. It means the community doesn't have to recover so much compared with a house that looks like this, that's completely lost its roof. So that in terms of benefit, there's a very significant benefit that accrues from that extra expenditure. And the balancing act is presenting the science that says, yes, this is a likely scenario, so that the foregone losses are real losses, particularly in the light of climate change. And this is why we lean on Hamish and his team to advise us, because we've got to look into a crystal ball and say, what are the cyclone tracks of the next 50 years, which is when the buildings we build now are going to be loaded.
Yeah, thanks, Jeff. And possibly another question for you, but maybe Hamish has a comment as well, is are we seeing this flow on already into insurance costs as well? And are insurance companies factoring in the potential changes in their pricing, do you think?
Yeah. That's a little bit out of my wheelhouse. But certainly insurance companies have to balance their books, and so they have to weigh up the level of risk that they're seeing at the moment, and also the level of risk that they're looking at down the track. And it's to their advantage to encourage us to build resilient buildings, so that in the future, if events happen, those buildings are less likely to present huge claims. We're not saying they're not going to present any claim at all. If you lose a window through because of some really heavy debris hitting the front of the building, you're still going to have repair work to do. So it's not going to be a case of no claims at all. You'll still have some claims, but the magnitude of the claim is not going to be anywhere near as severe because the roof is still on your building.
Yeah. Thanks, Jeff. There's a lot of questions about the actual. There's one question here that says, is there a way to estimate how much overall damage might increase with projected changes in tropical cyclone intensity? Is that something?
Yes.
Sorry, you can tell.
That is something that there's a profession that looks into. Yes. So actuaries are looking into that all of the time. That they have models. So if they have a model of what the hazard is, which is the tropical cyclone, what is the tropical cyclone likely to be, they can then use what they call vulnerability curves, which express what level of damage would you anticipate for a given wind speed into those models, and estimate the level of damage that happens. And they calibrate those models all of the time, so that already Narelle has been mentioned. As Narelle was approaching the coast, actuaries were running those models, trying to estimate what kind of losses would be anticipated. Then, of course, it happens, and they can say, well, here's how our anticipated losses compared with our real losses.
Yep. Just to add to that, even in academic circles, there's been a shift from just looking at trends in the actual hazard, so, rainfall or strong winds or storm surges, to trying to assess damage trends and projections of damage. So taking into account these other factors, which Jeff mentioned, the vulnerability and the exposure, looking at a more holistic picture of cyclone risk rather than just the actual hazard of the cyclone itself. And so, yeah, certainly, like in the last few years, been a number of papers coming out, looking at future trends in damage and things like that. So it's definitely, quite popular at the moment.
Yeah,
and it is.
Oh, you go. Sorry,
I was going to say, it is possible to model what a change in a building standard might look like, or a code or standard might look like, because that affects the vulnerability curve. So you can say, if we improve the strength of the building, we'd expect less damage for a given wind speed, adjust the vulnerability curve and then run the model again, and that shows the losses that you've prevented by that.
Yeah, and I think what we've demonstrated in the work that Hamish and yourself have done together, Jeff, is that how we measure what we mean by, how we measure tropical cyclone risk and where it is on the coast and how it is impacting damage. If it becomes a tropical low, it can still create a lot of damage and a lot of and we potentially in the academic circles don't measure it in the way. So working with Hamish, it's been great to see that, we're working with the impact and understanding how to measure that impact in a better way that's more meaningful and fit for purpose to what you need to change these wind loading standards in the future.
Ramona, there's a question in the chat about naming tropical cyclones. So just to answer that briefly, there's a predetermined list of names for each season, and I don't know if someone from the bureau's on the call, maybe they could pop it in the chat, but it goes out for several seasons, tropical cyclone seasons ahead. So maybe it's, I'm not sure, 3 to 5 years ahead. There's a list of names, and they just go through them alphabetically. And if you get to the end of the alphabet, as happened in the US hurricane season or tropical cyclone season, they had to start using Greek letters or something. Or I can't remember, but anyway, there's a full naming convention. So
yes, and I have, that's right. There are lots of questions we haven't covered, and some of them, Jeff, I wasn't sure. Because they're quite specific. So any comment on a change from a 3-second gust to a 0.2-second gust in the revisions of AS 11702 standard. So very specific. So I don't know.
Yep. Yeah, I can deal with that one. Yeah. In the really ancient days, back in the 1970s, most of the anemometers were what were called Dines anemometers, and they're the same principle of anemometer as on aircraft, a pitostatic tube. And that has got a really fast response rate. So all of the historical data back then was effectively a really short gust, a 0.2-second gust. As the automatic weather stations were introduced, they were programmed to deliver 3-second gusts. And a 3-second gust is a bigger gust, and it's a little bit slower than a 0.2-second gust. Once the Standards Committee realised that there was a difference between whether it was measured on an AWS or a Dines anemometer, we did a conversion so that everything was back to the really short gust, the 0.2-second gust. And that's an appropriate gust for a structural engineer to use because the size of that gust is commensurate with the structures that we're designing. So a really short 0.2-second gust is an appropriate gust to use to design things on buildings.
Thanks, Jeff. It's a great answer to that very specific question. I'm glad you could answer. There's also one in here, maybe that's more for you to comment on, Hamish. It says, given the climate projection of cyclones is challenging, is there any work going on in Australia or internationally to improve this and any national cyclone projection products currently under development that could help in practical decision making? Yeah. Very much so.
Yeah, definitely. So there's a lot of work happening at the moment, even under the Australian Climate Service project, which I'm involved in, and we've been looking at regional projections. So exactly looking at some of the aspects that I touched on today. Are tropical cyclones, do we expect them to move further south in the Coral Sea region? What about off the west coast of Australia? Are there differences? So there's a lot of local effort happening, both within CSIRO, at the universities, at the Bureau of Meteorology to tackle these questions. There's a lot of global effort. People all around the world are working on new modelling techniques, not just global climate models, which is kind of the crux of things like the IPCC assessment. But synthetic tropical cyclone tracks, which I haven't touched on, and people in the insurance industry will be very familiar with them, because it's one way to try to quantify risk is by simulating 10,000 possible tropical cyclones off the coast of Queensland, for instance, and looking at how they may shift in a future climate. So to answer your question, there's a lot of active research happening. It's a very challenging problem because of all the moving parts, which I hopefully touched on in my talk. In particular, the dynamics. So the jet, I think, is it meanders around a lot when it comes to sea surface temperature. Yes, there's changes and patterns as well, but it's less dynamic than the winds around the atmosphere. So there's lots going on. Yep.
Okay. Thank you. There's one more question we could probably answer, which is probably for Jeff. It's about adjusting the building codes to stronger and stronger winds will eventually become infeasible. Is it possible to cost effectively design buildings to withstand winds, or retrofitting existing stock to make them stronger?
The answer is yes to the retrofitting, and yes, it is feasible to design for higher wind speeds. So that already in WA, we've got wind region D, which are very high wind speeds, higher than region C, and it is possible to build cost effectively against those wind speeds. So it's not like there's some upper limit that we're going to reach where it's not feasible to design. So they're building lightweight steel buildings over there. It doesn't have to be a concrete bunker to handle those kind of wind speeds. And again, as long as you know what wind speed it is, it's a question of matching structural strength with the loads that you're going to be given. Possible to retrofit? Yes, it is possible to retrofit, but it's much more cost effective to design against it in the first place. So that when I mentioned that it costs a number of $1,000s to incorporate resilient measures into the design that's going to mean it can cope with that high internal pressure, if you were wanting to retrofit that, it would be a few tens of thousands of dollars, because you've got to pull things off and then reassemble stuff. And of course, if you don't do it, it may cost you hundreds of thousands, because you've got to rebuild your building at the end. So yes, it is possible to retrofit. It's even better to build it appropriately in the first place. And that's the best bang for buck that you can get. And that's why it's really important that codes and standards be kept up to date, and why it's really important that we look to people like Hamish and his teams for the excellent science that is going to underpin those changes that are going to mean Australia can respond in the most cost-effective way to the challenges of the future.
Great. Thank you so much. We're out of time, but thank you very much for all the answers to the questions. Your presentations were very engaging, and really for sharing all your wonderful knowledge with us. We really appreciate it. I wanted to thank everyone who's supported the Hub today by showing up to our presentations. Thank you. I hope you've learnt something. I hope that you understand how much we value co-design in the Hub. As Jeff said, if you want to read more about how we work with people like Jeff, we're going to put in the Q&A or in the chat the link to an article that Jeff's written that describes that work. We've got some great webinars coming up in the coming months, and you can go onto our website and join our newsletter so you can be notified of those. So use the QR code there. Please spread the word for people that you think are interested. And before we finish, we'd really like your feedback. So an email will be sent with a brief survey and it'll be put on the website when the recording is published. So please let us know if you want suggestions for future webinar topics and what you think of our webinars. We value your feedback. So So thanks again to Jeff and Hamish for your time, for all those behind the scenes who made this happen today, and see you next time. Thank you very much.
Thank you.
Thanks,
Thank
Jeff.
you.
Thanks, Hamish.